Welcome back, everyone. We are now here at the end of actually chapter 3, and there's one theorem left already here on the slide that we will prove, and this is really a Bolzano-Weierstrass theorem stating the following thing. So if you're in a reflexive Banach space, those are those spaces where the canonical map is surjective. So in other words, the bidual is isomorphic to the space itself. That isomorphism is also an isometry. Then it says every bounded sequence in that space has a weakly convergent subsequence. I already mentioned in the last video, without the word weakly there, then it's in general false. We will have a counterexample in the next chapter. So you really need that weaker notion of convergence. All right, so we will prove it now. And it will use the previous theorem, namely Helly's theorem about existence of weak starly convergent subsequences. All right, so let's get started. Let xn be a bounded sequence. This argument is very nice because it really combines so many things that we have assembled over the past videos. So define y as the set of all linear combinations of those sequence elements, so alpha j, xj, the alpha j in your underlying field, and capital N natural number, and you're going to take the closure. You will understand why in a few moments. Since y is a closed subspace, well, it's closed by construction because I close it up with all possible limit points, and it's a subspace because I look at linear combinations of elements. Right? It is now a closed subspace of a reflexive Banach space. Okay, remember, by assumption, our space X, this is a subspace of X, is a reflexive Banach space, and one of the properties of reflexive Banach spaces was that if you look at subspaces, closed subspaces, then they're also reflexive. Right? So that thing itself is a reflexive Banach space. Since Y is a closed subspace of a reflexive Banach space, Y is also reflexive. And moreover, I claim it is separable. Why is it separable? Well, why does it have a countable dense subset? Well, if you just look at the linear combinations with coefficients alpha j that are either rational numbers, if your field is the real number field, or complex numbers with rational, real, and imaginary part, if your underlying field is the complex number field, then these linear combinations will be dense in Y, and they are countable, right? Because the small n goes all the way up to capital N, which is countably infinite, and the rational numbers or complex numbers with rational, real, and imaginary part, they're also countable. All right? So these are separable. In turn, so it is a reflexive Banach space. That just means what I said earlier about the canonical map being now an isometric isomorphism. So in turn, the bidual is isomorphic to Y. And since the isomorphism in question, namely the canonical map, since the isomorphism J on Y to the bidual in question is an isometry, we know that, well, the double dual, the bidual, is also separable. Why is this? Well, you have a countable dense subset in Y, namely all these linear combinations here with the red arrow. So now what does the isomorphism do? Well, it maps it to a countable set. This is a linear thing in the bidual. And why is that thing still dense? Well, because it preserves the norm. J is an isometry, right? So things that are dense here in Y, like these guys up here, they're going to be dense in the bidual, right? So that's why the bidual is also separable. It has a countable dense subset, which is precisely the image of these linear combinations up here with the red arrow under the map J. Okay. So, but now remember, whenever you have a separable, when you have a Banach space and the dual space thereof is separable, then the space itself is also separable. That was one of the results much earlier. So now this means applied to here, to the bidual, we know that it's separable. So the, well, one star off from the bidual, this is just the dual, is separable, right? So is also separable. Okay, nice. Now what I'm going to do is I'm going to apply the theorem that we just proved before this one, namely Halley's theorem. Remember, that was a theorem for separable normed linear spaces, and now I'm going to use it for, well, this separable normed linear space, namely the dual space. Okay, now use Halley's theorem, okay, for the dual space, right? So if you have J sub xn, remember the xn's are bounded, and the canonical map is an isometry. So that means that sequence, J sub small xn, is a bounded sequence in the bidual, right? So this one has a weak starly convergent subsequence. This is Halley's theorem applied to the dual space of Y, which is separable in this setting. Okay, has a weak starly convergent subsequence since bounded. Right, let me write this out. I already said it in words. Xn, because it's an isometry. The canonical map is an isometry. Okay. Weak starly convergent subsequence. Let's denote it by J sub x sub n sub m, m1 infinity. So this is a subsequence of J sub xn, n1 infinity, with weak star limit, let's call it k. Say, right? Yeah, but remember, Y is reflexive, which is because it's a closed subspace of reflexive Banach space, so we know precisely how that K looks like. But Y is reflexive, so K is equal to, well, J of, say, x sub infinity for some element x infinity in Y, well, which is a subspace of X. Hence, for every f, for every bounded linear functional in the dual space of Y, what do we have? F, x, and m. Hopefully, if everything goes fine at the end of the day, this thing converges as m goes to infinity. And it does indeed, because this is, remember how these J sub x and m act. This is pointwise evaluation. Now J sub x and m converges to my k as m goes to infinity. That's what we had earlier. This is a consequence of Halley's selection theorem. So k of f, yeah, but k of f, because of this one, it is jx infinity f, and because of reflexivity, this is f of x infinity. Okay. As m tends to infinity. I already wrote this out. Okay, let's move it to the left. And this here. Okay, right? Yeah, but however, now this convergence was written down here for any bounded linear functional on the subspace Y, but it easily lifts to a bounded linear functional on x. And why is this? Yeah, because these elements here, x sub nm, where are they from? Well, they are of course from y, right? They are of course from the subspace y. So you have the same convergence if you act with a linear functional that is defined on the whole space, right? So however, this convergence extends to all bounded linear functionals on x. So indeed, you have that x sub nm converges weakly to x infinity as m goes infinity. This concludes our proof. All right? So this was a very nice combination of many things that we know about reflexive Banach spaces, the canonical map, its properties, in particular the isometry property, the isomorphism properties is crucial in this. And then we have to play around with the separability, realizing that the dual space is separable because of a theorem that comes from the separability of the bidual. And then once you have this, then you have to apply Helly's selection theorem, exploit again that you're in a reflexive Banach space Y. Then you have this line here, and then you have to realize, well, these elements here, the x sub nm's, they are in Y. So although this equation here is written out for any linear functional just defined on Y, is actually true then for any linear functional defined on all of x, because Y is a subspace of x, right? And that is then the weak convergence of this subsequence. All right, fantastic. So this guy we will use in the next chapter. It's very important. Okay, but now going to the next chapter, we will study more convergence types, this will now prepare the last chapter. So now this is chapter 4, and sort of in chapter 4, as you probably would expect, all things will now kind of converge onto some target, right? Whatever that is. Well, we will learn soon what it is. So we have discussed Hilbert spaces, we have discussed Banach spaces, and have assembled all the basic properties, and now we will all combine them in essentially in the spectral theory of operators and bounded linear transformations. So this section, chapter 4, which is called bounded operators, in the latter part is foremost concerned with what is called spectral theory. Okay. So eigenvalues will appear, eigenvectors, but much more. The theory is much richer than what you know from linear algebra. All right, so but let's get started. So first off, topologies and bounded operators. So we just discussed a few convergence types. Well, there's more, and we will start with the following ones. So let x and y be 2 NLS and Tn a sequence of bounded linear transformations. Okay, Tn a sequence, and likewise, well, what will turn out its limit in some sense also a bounded linear transformation. We say there's three types of three notions of convergence. Tn converges in, well, let's write it in red, in norm. That's the one that we already know what this is. Or uniformly. This will be, again, it will be a tower of convergence types. The one on top is the strongest, the one on the bottom the weakest. To T, if, well, Tn goes to T in operator norm, as n turns to infinity. Well, this looks a bit weird. Tn minus T in operator norm goes to 0 as n turns to infinity. All right, so that's the one that we kind of know of. Then the next weaker one converges strongly strongly to t if for all x in x, well, you have pointwise convergence. So Tnx minus t of x, now this is an element in y space, so y norm goes to 0 as n tends to infinity. Right, so if you were to compare this functions on the real or complex line, the property A would be the uniform convergence, that's why we call it uniformly convergent, and the second one would be pointwise convergence. Okay. The third one, well, there's also weak convergence here. Tn converges weakly to t if for all x in x bounded linear functionals on y, we have f tnx minus f tx goes to 0 as n goes to infinity. Okay, so that's the one. That's the one. Of course, now here might be some confusion. We had weak convergence in the previous sections of vectors in an arbitrary normed linear space. Now here we have weak convergence of bounded linear transformations, and bounded linear transformations, as you know, they also form a normed linear space. So this is just a maybe confusion on the surface. It will always be clear from the context which type of convergence you refer to when you say weak convergence. Okay. Good. Now, as I said, so this is again a tower of convergence. The one on top is the strongest, the one on the bottom is the weakest. Why is the one on top the strongest? Well, because for this simple inequality here, so by linearity of f, Tn and t, we have, well, f Tn x, start at the bottom, and hopefully we can estimate everything all the way to the top. So we have linearity of f says this is Tnx minus t of x evaluated on f. Then you do the standard thing, you estimate with your norms, Tnx minus t of x. So the first one is the operator norm of f, the second one is just the norm in y. Then you use the way how you define the vector space structure on the bounded linear transformations, which is pointwise. So you have this, and now you estimate one more time. You get the operator norm of f, the operator norm of the difference Tn with t, and then the ordinary norm on x of the element x, right? So, and that's why it's a tower, because if you have norm convergence, that is to say uniform convergence, this here and that here does not depend on n. So when n goes to infinity and you have uniform convergence, this will go to 0, so hence everything to the left of it has to go to 0. So in particular, it would mean this has to go to 0, which is the strong convergence, and this here has to go to 0, which is the weak convergence. Likewise, if you have only strong convergence, then you want to stop estimating at this point, at the yellow vertical bar. This here would go to 0, and hence this here on the left would go to 0. So strong convergence implies weak convergence. All right, so really it's a tower. The other directions are in general not true. So in general, you cannot conclude that weak convergence gives you strong convergence and that strong convergence gives you norm convergence. Here are some examples to convince you of that fact. Example, consider x LPN. You write, so these examples, this is sort of know by heart stuff. Standard examples why one convergence type is stronger than the other. So you look at these sequence spaces for any p from 1 including infinity. First, if Tn Lx is given by, well, x1, x2, x3 are sent to, well, the same thing, but everything divided by 1 over n, so that is in a sense a multiplication operator that we discussed very early on in this module, and multiplication is each term by 1 over n, which is bounded sequence for sure. And now what I claim is then Tn, okay, now let's first write the claim, then prove it. Then Tn goes to the 0 operator uniformly, since, well, obviously the operator norm of Tn minus 0 is 1 over n. Right? That immediately follows from this definition up here, and surely 1 over n is then goes to infinity, goes to 0. Okay, so here we have an example of a uniformly convergent sequence of bounded linear operators. Second, remember the shift operators, like in the first week. If L and R denote the, well, L is the left shift, that's why L, and R is the right shift, that's why R. So right shift moves your whole train 1 unit to the right and inserts a 0 in the first entry, and the left shift moves your train 1 unit to the left and erases the first entry. So the image sequence would start with x2 and then x3, x4, but x1 is gone. Right? So the left shift suppresses information, in other words. So that beats those shifts. Then let's look at Sn, following operator. So this is an n-fold composition of the left shift. So L to the power n, that means I compose L by itself n times. So let's think about it. So x1, x2 is sent to what? Well, if you do it once, if n is equal to 1, then you start here with with x sub 2, right? If you do it twice, you have to start with x sub 3, so on and so forth. So if you do it n times, you will start with x sub n plus 1, right? And then n plus 2, and then all the rest, right? So the first n elements are gone if you apply the left shift n times, right? Now this thing satisfies let's compute the operator norm, Snxp. Let's do it for p different from infinity so that I have honest sums, and then you can easily convince yourself this will be I from n plus 1, well, because you start with the n plus first here, all the way to infinity, x sub I p. Yeah, but since you're working here with p-summable sequences, this sum here is just the tail of a convergent series. So when n goes to infinity, Cauchy criterion tells you this will go to 0. All right, 4, 1, p away from infinity, and all x in LP. All right, so this tells us that Sn converges to the 0 operator strongly, but not uniformly. Why? Because I claim the operator norm of Sn is exactly equal to 1. So why is this? So remember how we computed the operator norm of S sub 1? We just found an estimate, it's at most equal to 1, then we found an element that hits it precisely, right? That makes the equality there. Yeah, but that element you can just modify to the n-fold iteration here, and well, then you will get that the operator norm is equal to 1. So you have strong convergence, but you don't have uniform convergence. Okay. The next one is easier. Right shift is always easier. Finally let AN denote, well, the n-fold iteration of the right shift. So R composed with itself n times. So what does this guy do? Well, it inserts now not just 1 0, but n zeros here out front. And what can we say about this? Then f a n x. So x is any element in LP and f is any bounded linear functional on LP. Yeah, but we know how these guys look like. We exactly classified the dual space of LP. We proved that this thing is isomorphic to LQ. So we have such a representation for sequence y in LQ. And that, of course, is by definition up here. You just use this. It is equal to k, n plus 1, and then x k minus n, y k. This goes to 0 by Hölder inequality as n goes to infinity for 1p less than infinity, where y is an element of LQ, LQn with 1 less than q less than infinity, and 1 over p plus 1 over q is equal to 1, right? So here we use that knowledge that we know precisely what the dual space of LP is, and this I need because I'm acting here with a functional on LP, right? So this is an element in LP n star, and I know how these look like. These are again these sums, these inner product looking type things, all right? So this shows that it converges weakly to 0. So AN goes to 0 operator weakly, but AN does not converge to 0 strongly or uniformly, since, and that's super easy, the operator norm of AN is clearly 1, because, well, all the information is still hidden here. It's just a bunch of zeros inserted up front, and likewise ANX in P norm is precisely equal to the P norm of X. Right, so again, this does not align well with a strong and uniform convergence to the 0 operator for any n in N and X in LPN. Alright, so these examples, they clearly show you that uniform convergence implies strong convergence, implies weak convergence. That's a general fact, and you in general cannot go upwards. Alright? Good, very nice. So that's the starting point. We will prove more results. We will then define more bounded linear transformations and then start developing spectral theory, which is very exciting very soon. I hope to see you then.